Okay, so I wanted to make a quick video. This is actually a control theory problem, and I'm working as an engineer now, and I recently finished school and everything, but I want to be able to remember these problems because I really enjoyed this subject of control theory. So I thought it'd be a good idea to just review, various problems that I've done throughout the class and show the viewer, show anybody who sees this, just some of the interesting things that you see within control theory and what these things represent. I think it was a really cool subject. I think it's a great exercise for the mind, and it's very visually pleasing. So what are we looking at here? Um, we're considering something called a system. We're going to call this system P1, and this maps each input U to these solutions Y, and this Y is an output. So what does that mean in real life? Well, usually you can model systems in real life kind of like this. This is something you'll often see in control theory. So you have some sort of input U to a system. So this is a system, and this system has some sort of output. And you can think of this as like a light switch, like the input to it is you flicking the switch on or off in, one state or another. The system is actually controlling the state. So the system is X is what we call the state of the system. And you can think of this as the circuit being closed or open. So when the circuit's closed, um, that means the current is flowing through the wire in the walls, and then you're going to get light in the room. When it's open, the room's dark. And why the output here is actually, the light bulb being turned on or off. So, you flick the switch on, the circuit closes, and then the light turns on in the room. You flick the switch off, the circuit opens, and the room goes dark. If you want to go more complex, it's like, the state could be a robot in an environment, and you, which is an input, could be like, oh, I want the robot to go to a certain position, or I want the robot to drive forward, right? And then the output would be the robot doing that. It would be the robot, the motor wheels turning, and then the robot drives forward. So, we're not going to dive too much into this. This is just a really useful thing. You can model a lot of things in the physical world with just this simple little sketch right here. So it's kind of cool. Anyways, let's jump back to here. What's all this, squares and numbers and everything? This is actually something that we've all seen maybe in high school. This is a set of linear equations written in matrix form. So these little dots here are something called the dynamics, right? So again, X is like the system state. So that shows up here. And perhaps you're keeping track of two different things within your system. So we have an X1 and an X2. U is the input to the system, and Y is the output to the system. So this whole thing we're looking at here is actually this guy right here. It's like a relationship between an input and an output. And in control theory, we call this state space representation. As we do this problem, it'll be a little bit more clear why we write it this way. And our goal for this problem is going to be to draw this as something called a block diagram. So it's going to be like this guy right here, but it's going to be a little bit more expanded. But it's, the same thing. Keep in mind that it's still this little simple block diagram with an input and an output. We're just going to kind of look at the mechanisms inside the internals. And so we're going to draw this as a block diagram using something called an integrator, summations, and gains. Okay. If you don't know what integration is, it's like keeping track of change over time of some sort of function. Maybe you've taken calculus before, maybe you haven't, but the thing to keep in mind is it keeps track of how something changes over time, and then keeps track of like the whole total change. Summation is simple. It's like adding two things. That's all you have to think about. Gains is like multiplying something. That's all you really have to think about. If you know electrical engineering, this is like how you amplify something, amplify some sort of input. But okay, so why do we write this? And this is called state space representation. Okay, why do we use this? Well, if you know matrix multiplication, you might be able to see past the matrices here. And by the way, we call these rectangles matrices. What we can do actually is perform something called matrix multiplication and expand this out, and it'll become more clear why I said earlier this is another form of a linear system, or like linear equations. So let's go ahead and write this out actually as a set of linear equations, and that makes it easy to do our objective, which is drawing a block diagram. Okay, so the first step is going to be writing that system. So let's go ahead and do that. We have, you know, if you know matrix multiplication. If you don't worry. What I'm going to do is basically take this and write it as a set of equations. You don't need to know the middle steps. If you do know this, you should be able to follow along fairly easy. This is a simple problem. So here we have, you know, x1 dot, which is the change in x1, or the change in the first thing we're tracking within the state, is equal to, you know, if you do your basic matrix multiplication, it's the first row times the first entry plus the second, you know, column entry times the second row here. So let's go ahead and write that out. It'll be a little bit more clear. So we'll say like expanding this is actually going to come out to x1 dot is equal to x1, right? Or 2 times x1 here. So 2 times x1 plus 0 times x2. So we don't have to write that, but it's plus 0 times x2. So that's our first equation. And then we have to also take care of this over here. So it's plus 3 times u. Okay. So plus 3 times u. Let's take care of our second equation, which is x2 dot. So what does this come out to? x2 dot equals, so let me point my finger, so even if you don't know matrix multiplication, you can kind of follow along with what I'm doing. It's going to be negative 1 times x1 plus 3 times x2. So negative 1 times x1, we'll just write it that way, plus 3 times x2. Plus, you know, let's not forget about this guy, plus 1 times u. So just plus u. Okay, so that's our second equation. And then let's take care of this guy down here. And this is actually just going to come out to one equation when you do the multiplication. So we're going to have y equals, right, 1 times x1 plus 4 times x2. So x1 plus 4 times x2. Okay. So you see how this is one and the same. These are just two different forms of the same thing, which is a set of linear equations. A lot of systems in the world can be modeled as a set of linear equations, which is why this form right here is just nicer to look at. You don't have all the confusion and all the multiplications and all that. It's just like nice and compact here. As you get deeper into control theory, you see why you write it in this way when you're talking about eigenvalues, when you're talking about stability. You know, this is really essential to write it this way, because then you can just do certain things to look at this matrix here and yada yada, but we won't worry about that. We'll come to that in a later video when we do some more advanced problems. For now, we just noticed that, boom, this guy can be written like that. So let's go ahead and do our objective here, which is draw this as a block diagram using integrators, summations, and gains. So I like to take care of the integrators first. So let's go ahead and maybe I'll put this here. Let me fold this so we can keep an eye on those equations as we draw this. Put that there. I'm gonna cover this up a little bit. Okay, so we have our set of equations here, and why do we draw it that way? Well, check this out. And this might be a little confusing, but in the end, we'll draw, follow the pathways, and you'll see exactly that the block diagram that we draw is this set of equations, okay? So let's start with our integrators here, right? And the first one we see is x1 dot is, here. So we have x1 dot. And this is clearly going into some sort of integrator. Well, that's how you write an integrator block. And then what comes out of it? Well, you're integrating this, right? And that dot actually represents, like I was saying, change, or in mathematical terms, we call that a derivative, right? So when you integrate a derivative, the original thing comes back out. So when you integrate x1 dot, x1 should come out on the other side, right? And perhaps let's maybe write x2 also. Let's take care of x2 dot. So we're going to have some other integrator block. And, this goes into here. And then out comes x2. And let's make sure we include our arrows so we get our directions correct here. So we have two things here, right? x1 dot turns into like x1. This shows up in this side of the equation. x2 dot shows up here. x2 shows up here. And then, because x1 and x2 are showing up a lot, and we get those from the integrator blocks. Okay, so that takes care of our integrator blocks. And now we got to check out our, well, I think it's a good idea to look at our gains, because that's a little bit easier. So the gains, again, are multiplication. So we're clearly seeing that, u is a sort of input here. So we'll say it's coming in like that somewhere. And the first time we see, some sort of integration here, we're seeing like it's being put to a gain of 3, or it's being multiplied by 3. So it's clearly going into this block here. And all we do is put the number inside. So on the output of this, u goes in, it gets multiplied by 3, and this is going to be 3u right here on this output. All right, so maybe I'll just write that for clarity. 3u is right there. And this is going in, and that's the output here. And then, this is getting added to 2 times x1. So how do we take care of that? Well, we can basically, put a summer block here. That's going to take care of that plus sign that shows up. And then how do we integrate this 2x1, right? We have to do 2x1 plus 3u. Well, we have the 3u. We need to be adding 2 times x1. And where does x1 show up? Well, it's right here, right? So perhaps we need to draw a line here, put a gain of 2, because it's 2 times x1, and then feed that into the summation block, right? So now we just took care of that first equation. This is what that first equation looks like in block diagram form. If this is the first time you're seeing this, it's a little trippy, but it's super interesting. Now let's take care of x2 dot. So we have, negative, we have negative 1 times x1 here. So x1's clearly being multiplied by negative 1 at some point. So perhaps we just put that here, negative 1. And this is being added. Let's draw a line. All right. This is being added. We have negative x1 plus 3 times x2. Well, again, where does x2 show up? It's down here, right? And obviously we're running it through another gain block of 3. So 3 times x2. And we're adding that to negative 1 times x1. Right, so this is negative x1, and x2 is going into here, and out comes 3 times x2. And boom, we took care of those two terms. And then the last thing we're adding is u, right? So let's just draw a line from here and input it directly into there. And, things are getting a little crazy now, but what we just did is negative x1 plus, 3 times x2 plus u. It's cool. It's like a circuit almost, It's like a circuit. It's a system form or a block diagram representation. Okay, so the last thing we're going to be looking at now is we're going to take care of y. So y is clearly, some sort of sum of something. So let's put it here. And the output is y. And, this is the output of the sum here. So we have to write it as the output of the sum of those 3 in the second equation. So y, right? It's the sum of x1 plus 4 times x2. So we're obviously going to be passing x1 here into this. So we can just draw a line directly from x1, pass it in right there, and then plus 4 times x2. So again, we have x2 here. Let's run it through a gain block of 4. And, yeah, we have it right. And if it's not clear, this is 4x2 on that line, and this is x1. So we have y equals x1 plus 4 times x2, or x2 times 4 being fed in, and that's y, right? So what you're looking at here is actually a block diagram representation of this system of linear equations. And it's kind of just a cool, very useful artistic form of a way to represent linear equations. If you have a bunch of linear equations, obviously you're probably not going to draw this out, but this is just kind of a interesting thing to see, right? Everything makes sense. So let's go over it one more time so you kind of translate it correctly. So x1 dot right here is equal to 2 times x1. So x1 times 2 gets fed into the sum, plus u times 3, right? And that's our first equation. Then we have x2 dot, which, is x2 dot is equal to it's an output of some sort of sum, right? Which is negative 1 times x1. So we have negative 1 times x1 being fed into the sum, plus 3 times x2. So x2 is over here, 3 times x2 sum, plus u, which we just tapped directly and feed it into the sum. And then y over here is equal to x1. So we just tapped this, fed it directly into the sum, plus 4 times x2. So we tapped the x2 node times 4 times x2. So, and the output is y, right? And again, you're seeing we're kind of using this input-output relationship over and over. That thing we looked at earlier, which is this, right? Input, output. So just really interesting. It's that what you're looking at here is the same thing as this, and it's also the same thing as this, and it's like this trinity form. In control theory, you can represent systems in different forms, and they all have their advantages and disadvantages. This one has advantages when you're trying to do linear algebra and like analysis of the system. This one is just nice to look at to see the relationships, and this one is just the most common representation that we might all be familiar with, like a linear system. So I just thought this was an interesting problem. I'll probably upload more of these, and I just really enjoyed control theory. I thought it was just a beautiful segment of mathematics. So that's it for this video. Hope you enjoyed, and I'll see you in the next one.